Hello there, this is a geometry video. It is chapter 8, section 2, and today we get to talk about the Pythagorean theorem and its converse. And so the first thing we have to do when we talk about Pythagorean theorem is we have to make sure that you are familiar with a right triangle, because the Pythagorean theorem relates to a right triangle. So over here on the left, if you will with me first, I want to make sure that we cover the anatomy of a right triangle. The hypotenuse is basically, and in most cases, a right triangle will have two legs. I shouldn't say most cases, all right triangles will have two legs and a hypotenuse. But I was going to say that in most cases, you have a short leg and a long leg, and you can tell that in this case the long leg is AC, the short leg is BC. But sometimes in the case of an isosceles right triangle, the legs are the same. But that's not neither here nor there, just some information for you. But all right triangles have a hypotenuse, and the hypotenuse is always the longest leg, or sorry, the longest side of a right triangle, and it is always opposite the 90-degree angle. So here's my 90-degree angle, and opposite the 90-degree angle is the hypotenuse. So it's very important that you identify where the hypotenuse is, and then the legs can be in either order, but the hypotenuse has to be in a specific order, so that's why I want to make sure that you always locate the hypotenuse by the fact that it's always opposite the right angle. So we have two legs and a hypotenuse, and the legs and the hypotenuse all have names, so we name leg A because it's opposite angle A, and leg B is opposite angle B, and leg C is opposite angle C. So the Pythagorean theorem states that in a right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. And again, that might sound pretty complicated when you read it the first time, maybe even when you read it the second time. But it's a lot easier to just kind of remember the formula here. Basically, it's telling us that if triangle ABC is in fact a right triangle, and if the right angle is angle C, then basically what we're saying is that A squared, one of the legs, A squared, plus the other leg squared, is equal to the hypotenuse squared. So sometimes you'll even notice that this formula will be written as leg squared plus leg squared equals hypotenuse squared. A lot of times you'll see that it's written this way: leg squared plus leg squared equals hypotenuse squared. However you choose to, so it's very important that it's always equal to the hypotenuse. Sometimes students will put the hypotenuse over here on the wrong side of the equation, and they get negative answers, they get crazy answers. So I'm trying to avoid that happening with you guys. So I want to make sure that you always identify where the hypotenuse is, and that it's always equal to the hypotenuse. So we're going to go ahead and get started with this. It says here in example 1, find x. And of course we have some right triangles in this case. And one of the first things you want to do is always identify your hypotenuse. Always opposite the right angle. Once I've done that, I can start to set up my equation. Leg squared plus leg squared equals hypotenuse squared. So my legs in this case, if this is my hypotenuse, then my legs are 6 and 15. It doesn't matter which order I put them in, but 6 squared plus 15 squared should equal my hypotenuse. It does matter where you put the hypotenuse. So always equal the hypotenuse. In this case, you'll notice that my x is one of my legs because the hypotenuse is 11. But nonetheless, I always write leg squared plus the other leg squared equals hypotenuse squared. So see, it's very important where you put the x. The x is not always going to be the hypotenuse, and it's not always going to be a leg. It could be either or. So in either case, you always set the equation correctly. So in this case, we're going to get x squared. 9 times 9 is 81, and 11 times 11 is 121. Then we subtract 81 from both sides. And 121 minus 81 is going to equal 40. Oops, losing my pen here. Take the square root of that, and x is going to equal, 40 is basically 4 times 10. The square root of 4 is 2. So we're going to get 2 root 10, which is approximately 6.325. But I really do prefer that you write the exact answer, which is 2 root 10. Okay, now in this case, 6 squared is 36, and 15 squared is 225. And then 225 plus 36 is 261. Square root. And the square root of 261, let's see, 261 divided by, okay, so it turns out that 261 can break down into 9 times 29. And the square root of 9 is 3. So we get x equals 3 root 29. And that is approximately 16.155. But again, I would really prefer that you leave the answer in its exact form, which is 3 root 29. Alright, so now we'll let you try this do-it-yourself question, and then we're going to go to what we call Pythagorean triples. You might have heard of them already. Pythagorean triple is basically a set of 3 non-zero whole numbers. First of all, if you remember anything about the whole numbers are all of the natural numbers with the inclusion of 0, and yet they're telling us that we can't use 0. So really what they're saying is that they want us to use only counting numbers. We don't want any negatives. So as long as you have 3 of those counting numbers, we'll call them A, B, and C, such that A squared plus B squared equals C squared. In other words, it comes out to a nice round natural number, as opposed to our previous examples where the third side ended up being some decimal. In this case, it turns out that 3 squared, which is 9, and 4 squared, which is 16, added together is 25, which is the same thing as 5 squared. The same is true for 5, 12, and 13, 8, 15, and 17, and 7, 24, and 25. These are some of the most common Pythagorean triples. You can also generate more Pythagorean triples by including all of the multiples of these that are already here. So for example, if you took 3 and times it, if you took all of these numbers and times them by 2, you would get 6, 8, and 10, and that would also work. You could also times all these numbers by 3, and you would get 9, 12, and 15. In other words, anytime you multiply 3, 4x, and 5x. So 3 times any factor, if you multiply all of them by the same factor, you're going to basically get a Pythagorean triple. Same is true for all of these. So in this case, it would be 5x, 12x, and 13x. Excuse me. 8x, 15x, and 17x. And then over here we have 7x, 24x, and 25x. And so you could always generate more Pythagorean triples by taking all of those numbers and timesing it by the same factor. So x could be 5 or 7 or 10 or 12 or whatever, and you would get another set of Pythagorean triples. So we're going to apply some Pythagorean triples here. It says use a Pythagorean triple to find x. Explain your reasoning. So what we're going to do is we're going to look at the 15 and the 12, and we're going to notice that both of these numbers are divisible by 3. So it turns out that 15 is equivalent to 3 times 5. And also that 12 is the same thing as 3 times 4. And I look at the 5 and the 4, and I'm thinking, we have a triple that is 3, 5, 4. Or sorry, 3, 4, 5. That's this one right here, 3, 4, 5. Oops, I went the wrong way. 3, 4, 5. So if this is 4 and 5, what we're missing is, sorry about that, we're missing the 3. Alrighty. We have a 3, 4, 5 Pythagorean triple, and this one's all being multiplied by 3, so we'll multiply the last one by 3, and that'll give us 9. So it turns out that x equals 9, and that will complete the Pythagorean triple. So now the Pythagorean triple is 9, 12, and 15. But x is equal to 9. They wanted us to find x, so x is going to equal 9. Alrighty, so using the same method, we want you to try these two. And then we're going to move on to our next example. And here it is. Damon is locked out of his house. The only open window is on the second floor, which is 12 feet above the ground. He needs to borrow a ladder from his neighbor. If he must place the ladder 5 feet from the house to avoid some bushes, what length of ladder does Damon need? And I know what you're all thinking. I mean, who doesn't do a math problem when they're stuck outside of their house? Of course, that's the first thing that you would do. Just kidding. But anyhow, the diagram in the book is a lot better, but basically we know that the distance vertically is 12 to get to the second floor window. Because of the bushes, we've got 5 feet here, and we're trying to figure out how long this ladder needs to be in order for him to be able to reach the window and get into his house. All right, so we have basically a right triangle set up because we have the house, the wall, the house, and the floor. It makes a 90-degree angle. And so because we identify our hypotenuse always opposite the right angle, we can set up Pythagorean theorem. We can say leg squared plus leg squared equals hypotenuse squared. All right, but also we can probably recognize that we need to do some work here. So I'm pretty sure that my answer is going to be 13. We can use a Pythagorean triple in this case. You could also just solve it. But what we see here is that we've got 5, 12, and 5, 12, 13 is one of our Pythagorean triples. So already we could just say, yay, answer is x equals 13 because of the Pythagorean triple. But if we didn't know that, if we didn't recognize it right away, you could still solve it. 5 squared is 25, and 12 squared is 144. And if we add 144 to 25, we would get 169. And then we square root both sides, and it turns out that the square root of 169 is also 13. So either way, you get 13 feet. The ladder needs to be 13 feet in order for Damon to be able to reach the window and get inside his house. Or he can just wait for his parents. So now you will try this do-it-yourself example. And I've gone ahead and drawn a diagram for you there. Hopefully that'll help you out. And then we're going to go to our converse. And the converse is nice because the converse of the Pythagorean theorem can help us classify triangles. So we know that basically if it's a right triangle, then the relationship a squared plus b squared equals c squared is present. The converse would be to go backwards from that. So instead of knowing that it's a right triangle, if this relationship exists, if a squared plus b squared equals c squared, then it tells us that the triangle is actually a right triangle. So instead of knowing that it's a right triangle from the get-go, the converse is backwards, and so it tells us that it's a right triangle as long as this relationship is preserved. So another way that we can use this is because we can use it to classify triangles. If I give you 3 different lengths, you can tell me if it's a right triangle, and thanks to the Pythagorean inequality theorems, which there's 2 of them, so we have them all here on the same slide, and I've kind of highlighted if a squared plus b squared equals c squared, then you know it's a right triangle. The inequality theorems are basically when it's greater than and less than. Same relationship. If a squared plus b squared is greater than c squared, so if the sum of the legs, if the sum of the squares of the legs is larger than the hypotenuse squared, then it's an acute triangle. And likewise, or on the flip side of that, I guess, if it's less than c squared, then it's obtuse. So basically we have equal to means that it's a right triangle if it's equal to c squared. If it's larger than the hypotenuse squared, it's acute. If it's less than the hypotenuse squared, it's obtuse. So we're going to use that information to classify these triangles over here. So what we have is here is our last example, and it says determine whether each set of numbers can be the measures of the sides of a triangle. And that, if you remember, requires that we do some checking. If you remember that in order for it to be a triangle, that's the triangle inequality theorem. That's the first part. We're not even classifying them yet. Is for us to say 7 plus 14 has to be larger than 16. 14 plus 16 has to be larger than 7. And then 7 and 16 has to be larger than 14. So if you remember, we have to, any two sides of the triangle has to be larger than the third side in order for it to be a triangle. And yes, 7 plus 14 is going to be 21. So 21 is bigger than 16, check. 14 plus 16 is going to be 30, larger than 7, check. And 7 plus 16 is going to be 23 and also larger than 14, so check. So that's how we determine whether or not it can be a triangle. Yes, it can. We do the same thing for our next example over here. We know that 9 plus 40 has to be larger than 41. 40 plus 41 has to be larger than 9. And then lastly, 9 plus 41 has to be larger than 40. And again, this is 49, definitely bigger than 41. 40 plus 41 is going to be 81, definitely larger than 9. And 9 plus 40 is going to be 50, definitely larger than 40. So in both cases, the triangles do exist. And therefore, now they want us to actually do this whole Pythagorean theorem thing. So what we're going to do is we're going to say 7 squared plus 14 squared, and we're going to compare it to 16 squared. Okay, so I'm leaving this big circle here to insert either an equal sign, a greater than symbol, or a less than symbol. Okay, you always want to make sure that the lengths of the sides are in order from smallest to biggest. So leg, hypotenuse is the question mark here. 16, it has to be along the side. The hypotenuse is always along the side. So they have to be in that order. Over here, same thing. We're going to go with 9 squared plus 40 squared, and then 41 squared. We're going to leave a big blank there in between the last two because that's where we're going to insert our symbol. So we know that 7 squared is 49, and 14 squared is 196, and 16 squared is 256. And then we know that 49 plus 196 is 245. And over here we have 256. So they're clearly not equal. And 245 is less than 256. And then over here, 9 squared is 81. 40 squared is going to be 1,600. And then 1,600 plus 81 is going to be 1,681. And 41 squared is 1,681. So in this case, they are in fact the same. So we know that B is a right triangle because they are equal. And in the case of the less than, this is going to be an obtuse. You'll notice, remember, that if it's a less than, it's going to be obtuse. An obtuse triangle, okay, because it's a less than. Had this been a greater than, then it would have been acute. So that is how you classify the triangles. And so now we're going to leave this last one for you. I will leave you with one note that when you are squaring these guys, when you go 2 root 3 squared, first of all, you should use parentheses if you're not. And when you do that, you need to square both the 2. So this would be 2 squared is 4. And then square root of 3 squared cancels the square root, and it's just times 3. So that would be 12. A lot of times students cancel the square root on the 3 and then forget to square the 2, and then they put 6. It's not 6, it would be 12. All right, so just a little hint for you there because you're going to do that 3 times in part B. Alrighty, so once you have completed this do-it-yourself question, you will have completed your notes for this lesson, and I will see you in class, and thanks for watching.